Hi everyone, I'm Jia Hao from National University of Singapore. It is my pleasure to present our work TEL, log-level suggestions via modeling multi-level code block information. This is a joint work with Jun, Xiang, Kaihang, and Zhengkai. As we all know, in recent years, modern systems have integrated into our daily life and become necessary. So, any minor incidents may result in serious consequences. For example, about 1 year ago, Facebook suffered from downtime. It affected millions of people. Additionally, in 2018, the Thin House was attacked and about 1.5 million individuals were affected. Based on this, one question comes up: how can we manage the reliability and security of software systems? One way to solve this problem is to observe system well, so that we can monitor or maintain system easily. Application log is a common source that records software running information. They can provide important indicators for software runtime status, and we can recover software behaviors with extracted information. In practice, software systems will print logs into files. Then we can analyze this information to do system monitoring, debugging, or maintenance. As a result, application logs facilitate system monitoring, debugging, and maintenance. Here is one logging statement from Zookeeper project. We can see it contains three main components: log level, which is used to distinguish different code contexts; static text describes the purpose of logging statements; and a dynamic variable records runtime execution information. When system running, logging statements will generate corresponding application logs. To generate high-quality logs, researchers focus on these three main components: log level, static text, and dynamic variable. In this work, we aim to suggest suitable log levels to generate high-quality application logs and help log analysis. There are 5 common levels for logging statements. They are trace, debug, info, warn, and error. In practice, developers can set a level for the system to decide which level's logs should be printed. For example, if we configure the level for the system as warn, the logs with lower levels, such as info, debug, will not be generated during system running. So if we set a lower level for a critical event, the system may not generate related log messages for this event. If we set a higher level for a trivial event, it will generate lots of false alarms. Therefore, it is important to suggest suitable log levels for logging statements, and this motivates our research question. Given a logging statement in source code, can we suggest a suitable log level for it? To suggest log levels, Praise work mainly investigates information of logged blocks. For example, which log level should developers choose for a new logging statement? It employs a regression model to infer log levels according to code block type and file name. For DeepIV, the state-of-the-art approach for log level suggestions, it utilizes a RNN model to predict log levels with log contents and code structures. These methods share a similar workflow. They first split the code snippet into different code blocks, and then use the information of the logged block to predict log levels. Furthermore, we find exciting work focuses on features inside one code block and ignores information from its surrounding code blocks. Based on this observation, we have a question: what is the key information that benefits log level suggestions? If we only consider intra-block information, is it enough? As we all know, logging statements describe program behavior by recording both intra-block and intra-block information when system running. Therefore, it is not enough to predict log levels if we only consider intra-block information. For example, both block 1 and 2 only have one logging statement sharing similar intra-block information. If we only use intra-block information to predict log levels, they are given the same level. However, if we can aggregate multi-level information, we can find their difference easily. Particularly, when we consider intra-block information, we can know block 3 interacts with block 1, and it is important since its calling function recreate socket address has many warning-level logging statements. While we didn't find any important signals from block 2's interacted blocks, such as block 4, so we should give a higher log level. for block 1. However, there are two challenges for us to predict log levels with multi-level information. First, how to encode multi-level code block information into one representation. Second, how to detail meaningful information for log level suggestions. To address these two challenges, we propose a new approach, TEL, to predict log levels by integrating both intra-block and intra-block information. We can see TEL contains two phases. First, build a joint representation to represent multi-level information, and then extract meaningful information for log level suggestions. The first problem we need to solve for TEL is how can we represent multi-level block information. Generally, we have two design choices for code block size, fine-grained basic block level or coarse-grained function level. And we have some observations about logging statements. First, we find functions reflect complicated program behaviors, and they may contain various logging statements at different levels. Second, we find most logged basic block, if not all, include only one logging statement. Last but not least, the logic of basic block is very simple and it is easy to represent. So it is reasonable for us to use basic block and their dependency to represent multi-level block information. Now we need to extract the intra-block and intra-block information. We know multiple representations of code have been developed to reason about different aspects of programs, such as abstract syntax tree, control flow graph, and call graph. For intra-block information, we use AST of basic block to capture related information. This is because AST can preserve semantic and syntactic knowledge of basic blocks. As for the intra-block information, control flow graph and call graph of a program reflect the potential execution paths. This provides a comprehensive semantics in the context of code blocks. So we combine CFG and CG as SFG to represent intra-block information. After that, we combine AST and SFG together to form a new joint representation flow of AST fast. For example, given a code fragment, we will generate the joint representation fast in the right figure. We can find it integrates the intra-block information in AST and the intra-block information in SFG. After encoding multi-level block information, we need to extract meaningful information for log-level prediction. As graph neural network proved to be powerful in modeling graph structure data, we designed to separate graph neural network to learn intra-block and intra-block information. Specifically, our proposed hierarchy block graph network contains three parts. First, it details intra-block information to parameterize each basic block as a vector. Second, it models intra-block information by propagating information from its neighbors. Last, it utilizes higher quality representations to suggest log levels. For intra-block information detailing, we know symbols and graph structures of AST encode semantics and syntax of basic block. The problem is how to pass it to capture intra-block information. Since graph neural network excels at extracting information from graph structured data, we utilize GNN's propagation and aggregation mechanism to extract intra-block features. After that, we generate the AST's embedding representation by average pooling so that we can keep important information in the basic block. By the first step, we have extracted the intra-block information for each basic block, and we know intra-block features can provide additional information for log-level suggestions. Now let's model the intra-block information. From the figure, we can see that the block for loop, we want to aggregate information from its neighbors. Consider the graph structure. We also use another graph neural network to propagate and aggregate the information. With the GNN, we can update the for loop representation with find leader and else block. After this process, we can generate high-quality representations for basic block that encodes both intra-block and intra-block information. In the last step, we use the representation of the logged blocks to suggest log levels. Particularly, given the logged block representation, we calculate a probability for each log level with an embedding, and then we suggest a proper log level for it. To evaluate TEL's effectiveness, we investigate its performance on 9 large-scale open-source systems from various domains, such as HBase and Kafka. Following previous work, we regard the log levels in these systems as our ground truth, since they are well maintained. To train our model, we randomly split logged blocks in each project into training, validation, and testing sites, and their proportions are 60%, 20%, and 20%. And we investigate TEL's performance by answering the following research question. First, how effective is TEL on log-level suggestions was state-of-the-art? Second, to what extent do intra-block and intra-block information benefit suggestions? Third, how well does TEL suggest log levels across systems? To answer the first research question, we compare TEL with DeepLV in accuracy, AUC, and AUD. The result refers the following table. DeepLV is the state-of-the-art that suggests log levels with intra-block information. In particular, accuracy is the corrected predicted log levels against all log levels. AUC measures the model's capability in distinguishing different classes, and AUD is defined by DeepLV. It measures the closing degree between predicted log levels and real levels. And the higher the value is, the better the approach is. From the result, we find TEL achieves higher accuracy, AUC, and AUD than DeepLV in all systems. We also explore how multi-level information contributes to log-level suggestions. For intra-block information, we compare 3 situations. Disable GNN. Use ASTN to extract intra-block information. ASTN is the state-of-the-art that extracts information from AITs, and our proposed GNN. For intra-block information, we consider 2 situations, disable GNN and our proposed GNN. From the table, we find that our approach achieves the best performance. This indicates both intra-block and intra-block information contribute to level suggestions, and our approach can extract this information well. We further explore TEL's ability to suggest levels in cross-system. In particular, we train HBGN on 8 arbitrary systems of the 9 large-scale systems and evaluate it in the remaining project. From this figure, we find TEL achieved promising results and performs better than DeepLV in cross systems. So we can conclude that TEL can be used to suggest log levels for new systems. In the end, we make a brief summary. We propose TEL to facilitate log-level suggestions. It encodes intra-block and intra-block information into a joint representation flow of AST. It utilizes hierarchical block graph network to extract information from FAST to suggest log levels. And it outperforms the state-of-the-art in terms of accuracy. We have released the source code of TEL at GitHub repo. And the key insight of TEL is multi-level code block information benefits log-level suggestions, and GNNs excel at extracting useful information from programs. Thank you for your attention. I'm happy to take questions.